S1L24 is about proportions within triangles. So 24.1 introduces a new theorem called the triangle proportionality theorem. So starting in the upper left, triangle proportionality theorem says that if a line is parallel to one side of a triangle and it intersects the other two sides, then it divides those sides proportionally. So in the graphic, we have a line XY that is parallel to side BC, and that means that it cuts the remaining two sides AC and AB proportionally. So because of that, we can use those proportions to kind of solve for missing segments within triangles. So going through like kind of this step right here, we just talked about how, line XY is parallel to segment or side BC. And then because of that, we can set up those kind of like little portions, like the portions of the sides that have been kind of cut into smaller pieces. We can set up a proportion between those two sides. So like this says, let me erase these. This says AY, so AY over YC is equal to or proportional to AX over XB. So this comes in handy a lot of times if we have just like one little missing piece of the triangle, because we can set up basically an equation in this exact form in order to like solve for that missing piece. So we can set up a proportion, we can cross multiply in order to find that missing value. So that's what we're going to do in example 1. So example 1, we're given like a ton of information. So as I read through it, I'm going to go through and label it on the image as well. So it says that HG is parallel to CB. So HG is parallel to CB. HG is parallel to DE. And then DE is parallel to CV. So basically all of those segments that are like almost vertical, those are all parallel to each other. And then they also give us some segments, some little like pieces from the triangle. So DC is 4. So let's see, this segment right here is 4. And then AD is 12. So this kind of like longer segment down there, like from A to D is 12. GE is 4.5. So this little segment is 4.5. And then EB is 3. So from E to B has a distance of 3. And then we're supposed to find HD. So we want to find this piece right there. Okay, so we actually don't need all of the information that's given to us to find what HD is. We have enough information with just like basically excluding AD. We don't really need to use that full double section in order to find it, because we have kind of like two pairs of kind of they're not corresponding sides, but they kind of like match up. So like we have these two sides that go together, DC and EB, and then we have these two sides that go together, HD and GE. So we can set up a proportion saying that, they are equal, they are proportional, in order to solve for HD. So what that would look like, it's going to look really similar to this. It's going to look really similar to this up here. It's just going to have like different values initially. So I'm just going to use the letters for now. So it doesn't matter like what goes in the numerator. We just have to keep it consistent. So I'm going to say HD over, I'm going to use this side first. So HD over DC, and then that's going to be equal to, I'll use this side second, and then because HD was in the numerator, GE must go in the numerator, because that's kind of like the side that it's like opposite of, I guess. And then EB would go in the denominator, because that one kind of like matched up with DC. So we just have to keep it consistent. So like kind of, it's hard, we don't use the word corresponding in this situation because they're not like the same exact value, but like HD and DC, those are part of the same side, so they're same fraction. GE, EB, same side, same fraction. And then in terms of like ordering the fractions, like numerator and denominator, HD and GE, those are like kind of like I don't know, like the same panel almost, so that those were both in the numerator. And then DC and EB, those were kind of like the same panel as well, so those both go in the denominator. And we can switch the numerator and the denominator, but we'd have to switch both, so just keep that in mind. There's different ways of organizing this and like getting to the same answer, so if you organize a different way, it's totally fine. So now we are trying to solve for HD, so we don't know it. I am just going to go ahead and like replace it with an X just for making our equation a little bit more simple. So I'm going to put X in where HD was, and then DC, that was 4, so I'm going to put a 4 in for DC. And then that's equal to GE, which was 4.5. So I'm going to put a 4.5 in for GE, and then over EB, which was 3. So I'll put a 3 in for EB. And then now we have proportions, so I can go ahead and just solve by cross multiplying. So like that means that we go diagonally through the equal sign. So like one diagonal, that would be 3 times x, so that's 3x. And then the other diagonal is 4 times 4.5, which is 18, but I'm going to go ahead and just write 4 times 4.5 so we can see what the setup is. And then we can simplify, so I'm going to leave the 3x alone. I'm going to multiply the 4 times 4.5, which is 18. And then from there, our goal is to solve for x because we put an x for HD instead. So I just want to get x by itself. So I have a 3 that's being multiplied by the x, so I'd have to divide both sides by 3 to cancel out like the multiplication. And then I have x equals, because the 3 divided by 3 canceled out, and then the 18 divided by 3 is 6. So I have x equals 6, and x is what we use for HD, so we can say HD is equal to 6. Okay, so before we move on from this problem, this is kind of like a nice thing and a bad thing about these types of problems is that there is not one specific way to set them up. There's even multiple ways to do them. There's a video in the 24.1 workbook about how to do this, like in kind of like a more in-depth way. You'll see it takes a little bit longer, but if you wanted to check it out, you could. But just know, like, there's different ways to set it up. You just have to kind of like keep, I guess, like I said, like keep sides consistent with each other, keep like kind of panels consistent with each other in terms of like ordering your fractions. Okay, so 24.2, this is the converse of the triangle proportionality theorem, so just like switches it, essentially switches the order. So I'm going to go back up to the original theorem. So remember, converse just kind of like switches the hypothesis and the conclusion. So in the regular triangle proportionality theorem, this was the hypothesis. So, you know, if, and then it was line XY is parallel to BC, that's our hypothesis, then those sides or those segments of the sides are proportional. So the converse is just going to switch those. So it's going to say if the sides are proportional, then the lines must be parallel. So if we go down to 24.2, converse of the triangle proportionality theorem, if a line divides two sides of a triangle proportionally, then that line is parallel to the third side. So like I said, we just kind of switched. This is basically saying, you know, if those segments are cut proportionally, then the lines must be parallel, or XY must be parallel to BC. So in this case, you would essentially be given different, kind of like reverse information. So in like example 1 from 24.1, like at the top of the screen, we were given that the lines were parallel and we had to find missing segments. With the converse, you would be given the proportional sides and you would have to use those proportional sides to show that the lines were parallel. So example 1, determine if, let's just say line XY is parallel to BC. We can do that by setting up our proportion. Again, we just need some sort of consistency in terms of how we set up our proportion. So like if we want to start with, say, AX, I can say AX over XB. That'll be like side 1's fraction. And then side 2, because I put ax in the numerator, I would have to put ay in the numerator. And then because I put xb in the denominator, I would have to put yc in the denominator. So that's what I kind of mean in terms of like keeping things in proportion, because, you know, if I like, let's say I switched it and I put like ay and like xb kind of with each other, then that's pairing up like the shorter portion and the longer portion, so that wouldn't work. So you just want to make sure that you're pairing up kind of like the parts that go together. They're not like corresponding, but they are kind of like matching up, kind of like in this case, left side of the triangle, right side of the triangle. Okay, so now we can actually put in the values. So ax, that was 1.5, so we'll put a 1.5 in for ax. And then xb, that was 2.5, so we'll put that in for xb. Kind of looks like an 8. And then for ay, that was 2.1. And then for yc is 3.5. So there's a couple different ways that we can do it. One is just by like simplifying each fraction, so probably changing them both to like decimal form, so dividing both, so and making sure that they're equal. So like the first one, we could do 1.5 divided by 2.5, which is 0.6. And then the other one is 2.1 divided by 3.5, which is also 0.6. So each one is like kind of the ratio of the pairs of sides, and those ratios are equal, meaning that they're proportional. So this, getting like the two ratios to equal, would be enough to say that xy is parallel to BC. And then one of the other ways that you can do it, just in terms of like if you get really into like the habit of cross multiplying like we did for the earlier example, you can cross multiply here too. You should get both sides being equal to each other. So I'm gonna do that just kind of like off to the side to show you how it does work out. You won't get 0.6, but you should get two products that are equal. So if I were to take like 3.5 and multiply it by 1.5, 3.5 times 1.5 is 5.25. And then we should get the same like cross product from the other pair. So 2.5 times 2.1 . 2.5 times 2.1 is 5.25 as well. So it doesn't matter so much like what number you get, it only matters that they're equal. So like you can find it by like find out if they're proportional by like just simplifying each fraction directly and seeing if you get the same answer, or you can cross multiply. So like kind of, you know, if you accidentally like get in the habit of cross multiplying like we did in the previous example, like just know that you can find this problem out that way as well. Okay, so yes, line XY is parallel to BC.